Welcome back to AP Chemistry. Today we are going to talk about percent comp, empirical, and molecular formulas, and hydrates as well. So today you need a calculator and a periodic table, and then of course something to write on and something to write with. Let's get to it. All right, guys. So today, cool. So we're going to start with percent composition. Today's note should mostly be review with maybe a few kind of new concepts sprinkled in. Just like we talked about, the first 2 units are mostly all review. So we're going to start with percent comp. So percent comp, we are typically going to find percentage by mass of certain elements in a compound. We just compare the mass of those elements compared to the total mass of the entire compound. Most of the time we use molar mass, but if you're given a sample, you can use that as well. So first things first is write a correct formula for the compound in the question. So guys, you may want to review your naming rules if you haven't looked over them since, literally last year, or some of you maybe even 2 years ago. You probably want to review your naming rules, especially if after we name a few compounds, you're like, I have no idea what you are doing. It'd be a really good idea to look over those. Feel free to email us if you need a copy of naming rules or anything. And then you'll find the molar mass of the entire compound. So find molar mass. You do that by adding up all your masses from your periodic table. Once again, I would highly recommend printing off the AP periodic table. It's linked on Canvas, but you can also just Google AP Chemistry periodic table. The College Board one should pull up for you. Then you'll divide the total mass of the element by the total mass of the entire compound. I always think of this and remember part over whole. So anytime we're multiplying whatever part over whole if we're trying to get a percent. Multiply by 100. And then this, guys, there's no significant digits except for the masses. They've already been rounded. So just express your answer to 2 decimal places. Make sure to always include a percent sign. All right, so we're going to start with this. I guess this messed up whenever it converted, but that should be a black dot right there in between the two. So I don't know. Sometimes things mess up when they convert into Cami. Wow, cool. All right, so first question is about a hydrate. We're going to talk about hydrates later, but basically it's an ionic compound that has water kind of trapped in it. And so water is included in the molar mass. So first question says find the percent water. So we're looking for how much water is in the hydrate zinc sulfate heptahydrate. And then there's our formula for us. So first things first, we need to find the molar mass of our compound. And in this case, we're going to find the molar mass of our zinc sulfate and of our water. So I'm going to start with our zinc sulfate. So our zinc sulfate is made up of zinc, sulfur, and oxygen. First, we have 1 zinc, and zinc's mass from the periodic table is 65.38. We have 1 sulfur, and sulfur's mass from the periodic table is 32.06. And then finally, last but certainly not least, is oxygen. Now we have 4 oxygens, so that little subscript there, and each oxygen has a mass of 16. So that tells me my zinc sulfate, add those all together. My zinc sulfate has a mass of 161.44. All right. We also have to find the molar mass of our water. So our water is made up of hydrogen, and there's 2 hydrogens. Each of them have a mass of 1.008. And then we have oxygen, and we have 1 oxygen, and it has a mass of 16.0. So that gives me water's total mass is 18.016. So the thing is, though, there's not 1 water in my formula. There are 7. So I need to multiply that mass by 7. All right? So to get our total mass, we're going to add the mass of our zinc sulfate and the mass of our water all together. So 161.44 plus 18.016 times 7. Add it all up, and I got 287.552 as my total mass. we want to find the percent water. So we're going to plug that 18.016 times 7 in for our percent water. So that is 126.112. It's a percent, so multiply by 100. Plug it into your calculator to solve. And I got 43.86%. Remember, just always round to 2 decimal places here with the percent components. Okay, our next one says, what is the percentage of sodium in sodium phosphate? Okay, so first things first, we have to write the formula for sodium phosphate. So sodium is Na with a +1 charge. Phosphate is a polyatomic ion. It's PO4 -3. You do have to have your polyatomic ions memorized for the AP exam. So if you don't have that, that should also be linked on Canvas. Download that polyatomic ion list and start memorizing, especially if you've forgotten. I've also made a Quizlet, so I'll make sure I link that on Canvas for y'all as well, so that you can practice with a Quizlet as well if you want to. All right, swap, drop, reduce, and we get that our formula is Na3. It's terrible handwriting on my part. Na3 PO4. All right, so let's find our molar mass. So we have sodium, and we have 3 sodiums. And then we have phosphorus, and we have oxygen. We have 1 phosphorus and 4 oxygens. So the molar mass of sodium from the periodic table is 22.99 times the molar mass of phosphorus is 30.97, and then oxygen is 16.00. All right. Add those all up, and we get our total molar mass to be 163.94. All right, and then we want to know of sodium. So 3 sodiums times 22.99 gives us 68.97 times 100. Plug it into your calculator, and I got 42.07% sodium. Obviously, that top one would be percent water if you wanted to write that. All right, last one. This is also kind of percent comp, but on this one, we can actually use our mole-to-mole ratio instead of solving using our percent. So I want to know how many grams of magnesium there are in 50 grams of magnesium sulfide. First things first, got to write that formula. So magnesium is Mg, has a +2 charge. Sulfide is sulfur, -2 charge. Swap, drop, reduce. And you get MgS as our formula. Okay, so we're going to, number 1, take what's given. So I have 50 grams of magnesium sulfide. All right, if I have grams of magnesium sulfide, I need to drop that unit low. All right, and I'm going to use my molar mass here. So that is 56.36 grams is my molar mass of magnesium sulfide. It's 1 mole of magnesium sulfide. And then moles of magnesium sulfide is not what I want, so drop it low. 1 mole of magnesium sulfide contains 1 mole of magnesium. That's just because there's that 1-to-1 ratio of magnesium to sulfur. So that's why that comes from. And then moles of magnesium is not what I want. I want grams. So 1 mole of magnesium is equal to the molar mass of magnesium, which is 24.30 grams. That is grams of magnesium. That is what I want. So now I can multiply across the top, divide by the bottom, and I got 21.6 grams of magnesium. Okay, so that is kind of like a percent comp question there, but we can use that mole-to-mole ratio instead of solving for percent comp to figure out how much magnesium is there, but it's using those mole-to-mole ratios still. Okay, all right. Now then we're going to talk about empirical and molecular formulas. So empirical is the simplest whole number ratio of atoms in a compound. So like if I had talk about like glucose, for example, glucose is C6H12O6. So the simplest whole number ratio for that, its empirical formula would be C1H2O1. Okay, it's just the simplest whole number ratio. And then these are the steps. Guys, I'm going to go through the just quick steps with y'all because this should be review and hopefully it'll be a really quick refresher for y'all. But kind of the way we've always taught it. And if you are like, I'm not sure I understand, read through the whole steps. But you can read through the whole steps right there. But we go percent to gram, gram to mole, divide by the smallest, multiply till whole. So percent to gram, gram to mole, divide by the smallest, multiply till whole. All right. So I'm going to just kind of jump in because hopefully y'all will remember this as you're going. And then molecular formula is where we have our exact formula. So as opposed to empirical, molecular is like, where empirical would be like C1H2O1. Molecular is like the C6H12O6. It's the actual formula. So to figure that out, we just multiply our empirical formula by some factor. To figure out that factor, it's the molar mass of our molecular divided by the molar mass of our empirical. You often have to solve for the empirical before you can get the molecular. Okay, so we're going to start with a couple. Hopefully you'll catch on because I know we did a lot of practice with this last year. So at least at Heritage. So let's get started. So a sample of a compound contains 11.66 grams of iron and 5.01 grams of oxygen. We want to know what is the empirical formula of this compound. Step 1, percent to grams. We're already in grams, so we're good to go. If we weren't, we would just change our percent sign to grams, essentially. Just assume you have 100 grams, change it to that. So we're in grams. Great. Next, grams to moles. So I have 11.66 grams of iron, and I'm going to set up my railroad track and I'll fill it out in a second, and 5.01 grams of oxygen. All right, so grams to moles. So I don't want grams, so drop it low. And to get to moles, I'm going to use my molar mass. So the molar mass of iron is 55.85 grams of iron is 1 mole of iron. Plug that into your calculator. And guys, we're not super worried about sig figs here. Just keep about 4 to 5 sig figs. You don't need to round right now because we're going to eventually have a whole number. So if I do that, though, when I plug that into my calculator, I get 0.20877. Then I have 5.01 grams of oxygen. Grams of oxygen is not what I want, so I'm going to drop it low. Molar mass of oxygen is 16. 16 grams of oxygen is 1 mole of oxygen. Plug that in, and I got 0.3131. All right, now then I'm going to divide by the smallest. So 0.2 is smaller than 0.3, so I'm going to divide both of my numbers by this. All right, so if I divide that, it's 0.20877 divided by 0.20877. That gives me 1. 0.313 divided by 0.20877 gives me about 1.5. I think when I plugged it in, I got like 1.49. All right, but about 1.5. All right, so I've divided by the smallest. Last step is to multiply till whole. So I need to multiply these numbers to get a whole number. Since this is 0.5, to get it to be a whole number, I'm going to multiply both numbers by 2. And then those numbers that I end up with, my whole numbers, are going to be my subscripts in my ratio. So it'll be Fe2O3. Boom. Okay, so that's that. All right, let's do the next one. So it says a compound with a formula mass of 180 grams per mole all right, that's going to be important later, is found to be 31 grams of carbon, 5.20 grams of hydrogen, and 42.0 grams of oxygen. Find its molecular formula. So you guys notice we're trying to find our molecular formula here, but we don't have our empirical. So we have to find our empirical first, and then once we have our empirical, we can solve for our molecular. All right, so let's start by solving for our empirical. So percent to gram, done. We're already in grams. All right, so now grams to mole. So I'm going to have 31.0 grams of carbon. I know that for 12.01 grams of carbon is 1 mole of carbon. Plug that into your calculators, and I got 2.58. Then I have 5.20 grams of hydrogen, 1.008 grams of hydrogen is 1 mole of hydrogen. So that leaves me, when I plug that in, I get 5.1, erase, 5.158. And then oxygen, I had 42 grams of oxygen. For 16 grams of oxygen, it's 1 mole of oxygen. So I got 2.62. All right. I'm going to divide by my smallest number, so that is 2.58. And I ended up, obviously, when I divide 2.58 by itself, that gives me 1. All right, this gives me about 2, and then this gives me about 1 as well. So that tells me my empirical formula is CH2O. All right, now then I'm looking for my molecular formula. So I need to find that factor. So to find that factor, I need to divide my molar mass of my molecular formula, which is 180 grams, divided by the molar mass of my empirical formula. So to find my empirical formula, I'm going to add the masses of carbon, hydrogen, and oxygen. So carbon is 12.01 plus 2 times 1.008 plus 16. Add those all up, and I got that my molar mass would be 30.026. Divide by that, gives us our factor. Should be a whole number. So I got 6. I think it was like 5.98 or something like that. So rounds up to 6. All right, and then I'm just going to multiply my subscripts by that factor. So C, instead of 1, it would be C6, H12, O6. And there's my molecular formula. Okay, next one. All right. A sample of sulfur having a mass of 1.28 grams reacts with oxygen to form a compound with a mass of 3.20 grams. What is the empirical formula of the compound? Okay, so I know I have 1.28 grams of sulfur. I know it reacts with oxygen, and I know our total mass is 3.20. But I need to figure out my mass of my oxygen. So to do that, our compound is only made up of sulfur and oxygen. So if I know my total mass is 3.20 grams, I know that I had 1.28 grams of sulfur. So that gives me that my mass of oxygen would be 1.92 grams of oxygen. All right, so that's a little trickier, but hopefully you could have figured that out. I'm sure you could have. Y'all are smart. All right, so now percent to gram. Done. We're already in grams. Grams to mole. So I have 1.28 grams of sulfur. Know that my molar mass of sulfur is 32.06. I know that that would be 1 mole of sulfur. And I got, when I plugged that in, a real small number, 0.03992. And then my mass of oxygen is 1.92 grams of oxygen. Oxygen's mass is 16.0. It's 1 mole of oxygen. And so I got 0.12 there. So I'm going to divide by my smallest, which is this one. 0.03992. 0.03992. Obviously, when you divide it by itself, you get 1. And then for 0.12, I got 3. And they're both whole numbers already, so I can write my formula, which is SO3. Boom. Empirical formulas. Hopefully those are good. That was a good review. You guys kind of remember doing that. We did it right before Christmas at Heritage. All right. The last thing we're going to talk about is hydrates. And you guys are actually going to do a hydrate lab today as well. So I kind of talked about them a little bit already, but a hydrate is basically where water has become trapped in the ionic crystal lattice. So basically some of that is, the formula is ionic and some of it is water. The water isn't really bonded though to the ionic compound. So that's why we use the dot to separate the formulas instead of like writing them together, because they're not really bonded together. So basically when we are doing hydrate problems, we're trying to figure out how much water is trapped in the crystal lattice. So how many moles of water are in there per every like one ionic substance, how many waters are there in there? So that's what we're trying to do. So to do that, we need to figure out two things. Number one, the mass of the anhydrous compound. So anhydrous means like dry, no water. And then the mass of the water, which was trapped and evaporated off with heat. Basically, we can solve these pretty much the same way as we solve empirical formulas. Percent to gram, gram to mole, divide by the smallest, multiply to whole, but with two major differences. So instead of having two compound or all the different elements, we're basically going to use just the compounds. All right, so we'll have our salt and our water as our compounds there that we're using. And then we don't need to multiply to a whole because we should always get a whole number. So you don't need to multiply to a whole. All right. So this next problem is a very, very edited old FRQ from an AP exam, like super edited. All right. So it says, answer the following questions related to the gravimetric analysis. In the first two experiments, a student is assigned the task of determining the number of moles of water in 1 mole of magnesium chloride with some amount of water. That's what that N is there for. And remember, that should be a dot, but my computer didn't like when I transferred this. The student collects the data shown in the following table. So this is our data. So we have an empty container, our initial mass of our substance after first heating, second heating, and third heating. Okay, guys, so why are we heating this substance? What we're doing is we're trying to evaporate out the water. All right, so when we're heating our hydrate repeatedly, it's because we're trying to get rid of all of the water. So our first question says, why can our student correctly conclude that the hydrate was heated a sufficient number of times in the experiment? And that comes down to this part right here, is that our mass remained relatively constant, which tells us that we probably evaporated off all of our water. Guys, if we don't evaporate off all of our water, it could lead us to not thinking that there is enough water, so it could lead us to the wrong answer because our mass of our water would be too low and the mass of our compound would be too high. So basically, the mass stayed relatively constant between the second and third heating. So they probably evaporated all of the water. Boom. All right. So next thing we're going to do is we're going to use the data above to determine the formula and name of the hydrated compound. So first thing, we need to know two things. We need to know the mass of water that was used and the mass of the anhydrous salt. All right, so first let's figure out our mass of water. So to figure out our mass of our water, we are going to subtract our initial mass of our sample and container, and we are going to subtract it from the mass of our sample and container after the third heating, because that should be the difference, because it should tell us the difference between how much water we started with and then what's left after it's all been dissolved. So it should tell us the amount of water that we have. So our initial mass of water, or our initial mass of sample and container, it contained the water in it at that time, would be 25.825 grams, minus, after our third heating, all of our water should be evaporated, so minus 23.977 grams. All right, plug it into your calculator, and I got 1.848 grams. All right. Second thing we need to know is the mass of our salt. So mass of anhydrous salt. And to get this, we are going to subtract the mass of our empty container, or basically, yeah. So the mass here minus our empty container, because what should be left should just be our salt at that point. So 23.977 minus our empty container is 22.347 grams. And we should get 1.630 grams. Guys, it is important to keep that zero because of sig figs. All right, got to keep it. Sig figs are important. All right, so now we have our mass of water and we have our mass of our salt. So now we can go into our empirical formula here. So first step, percent to grams, already in grams. Check. Next step, gram to mole. So I have 1.848 grams of water. All right, and I know that I have that water weighs 18.016 grams. Once again, my handwriting is horrible. And I know that that is 1 mole of water. Plug it in, and I got 0.102575. And then my mass of my anhydrous salt is 1.630 grams. My anhydrous salt is magnesium chloride. Where did I get that from? Right here in the problem. All right. So the molar mass of magnesium chloride is 95.20 grams. And that should be equal to 1 mole. So go ahead and divide it. And when I did, I got 0.017121. So we got percent to grams, grams to moles. Now we need to divide by the smallest. So that's our smallest number. And here I got 1 and I got 6. So that means for every 1 magnesium chloride, there are 6 waters. So our formula would be MgCl2 dot 6H2O. And our name would be magnesium chloride hexahydrate, because we have 6 waters. All right, guys, that's hydrates. So you guys are actually going to do a hydrate lab. It's virtual. It's a video that you're going to watch. And then there's also a practice. Guys, the practice does have some multiple choice questions. In order to do your best service to help you prepare for the AP exam, I would highly suggest not using a calculator on the multiple choice practice questions that we give you guys, because you are not going to have a calculator on the AP exam. So do your best. All right. Bye.